This is the second type of induction, proof by induction. Okay, so we'll look at the actual proof part itself first of all. It says prove for all n an element of n, so it's all natural numbers, that 3 is a factor of this here. Okay, now looking back to the previous type of proof by induction, which was the series of numbers, the steps stay the exact same again this time. The only parts we need to fill in are the blanks in the middle. Okay, so the first step, prove the statement is true for all n equal to 1. Assume true for n equal to k. Then we're going to, based on this assumption, we must now show that the statement is true for n equal to k plus 1. We go down to the bottom and we can then say, therefore it is true for n equal to k plus 1, but since it is true for n equal to 1, it now must be true for all n equal to 1 plus 1, which is 2, and if it's true for n equal to 2, it must be true for n equal to 2 plus 1, which is 3, etc. Okay, so then therefore it is true for all values of n. So I haven't changed anything in the wording of those 4 steps. The only thing I need to do now is fill in the blanks for the first 3 steps. The first 2, very easy to fill in. It's the third one that we might have a bit more difficulty with, but at that stage you'll have 4.5 of the steps completed. Okay, so the first thing we need to do is to prove the statement true for n equal to 1. So to prove that it is true for n equal to 1, we're trying to show that this here is divisible by 3. We need to sub in, so it's going to be sub in n equal to 1, so it's going to be 4 to the power of 1 minus 1. 4 to the power of 1 is 4, so that's 4 minus 1, which is equal to 3, and then clearly 3 is divisible by 3, so that one is true. Second one, we're going to assume true for n equal to k, so it's going to be 3 is a factor of 4 to the power of k minus 1, and then it's going to be for k an element of n. Okay, so we're going to assume true that 3 is a factor of this bit here. Okay, and then it's going to be the third part. It says, based on this assumption, we must now show that the statement is true for all n equal to k plus 1. So it's going to be, is 3 a factor of 4 to the power of k plus 1 minus 1, and that's what we're going to try to show. So now what we need to do is this bit here, we're going to try to simplify it down and show that 3 does in fact divide unevenly into this bit here. Now in order to do that, the first thing we're going to do is split up our powers. So it's going to be, using our laws of indices, we can go and put it as 4 to the power of k by 4 to the power of 1 minus 1. Then what we can do at this stage, we can actually split this up as 4 to the power of k. Since we're trying to see that 3 divides unevenly, we're going to split the 4 into 3 plus 1, and then minus 1. And then we're going to write it as 3 by 4 to the power of k plus 1 by 4 to the power of k minus 1. And then on the left-hand side, we are going to do 3 to the power of 3 by 4 to the power of k. On the right-hand side, we're just going to keep this in brackets and leave it as 4 to the power of k minus 1. Now, hopefully you will recognize this bit here already. This one was part of our assumption up above. We've already assumed that this here, 3 is a factor of this. Now, if we're assuming that's true, then that has to be correct. So just to write down our conclusion for this part. So since this here first part, it clearly has to be divisible by 3 since 3 divides into it. And this here is assumed true, so the 4 to the power of k minus 1, we've assumed that is divisible by 3 from our assumption up above. Then therefore, the full thing together, 3 by 4 to the power of k plus 4 to the power of k minus 1 is divisible by 3. So then therefore, it is true for n equal to k plus 1. So then if it's true for n equal to k plus 1, we look at the rest of our assumption, but since it is true for n equal to 1, it now must be true for n equal to 1 plus 1, which is 2. And if it's true for n equal to 2, it is true for n equal to 2 plus 1, which is 3, etc. So it keeps going forever. And then therefore, it is true for all values of n. So like I said, the structure stays the same. The only part that changed compared to this proof, compared to the very first one, was this part here. Now this one is a bit easier than the working out of the other one, but it's still for both of them, it's still not that bad.